Multithreading in Java is a programming concept where multiple threads are used to perform multiple tasks concurrently. There are two ways to achieve multithreading in Java: by extending the thread class or implementing the runnable interface. Now, let's discuss the benefits of multithreading. The first benefit is improved performance. Multithreading allows efficient utilization of CPU resources by executing multiple tasks concurrently. The second benefit is a responsive user interface. Multithreading can be used to keep the user interface responsive while performing long-running tasks in the background. The third benefit is efficient resource utilization. Multithreading enables efficient utilization of system resources by allowing parallel execution of tasks. The fourth benefit is simplified development. Multithreading simplifies complex tasks by breaking them into smaller, independent parts that can be executed concurrently. And finally, the fifth benefit is enhanced scalability. Multithreading allows programs to handle large workloads by dividing them into smaller tasks that can be executed simultaneously. Let's now write a simple code snippet to understand multithreading in Java. First, we will create a class called Multithreading example that extends the thread class. Inside the run method of this class, we can write the code that we want to execute in a separate thread. Next, we will create a class called main where our main method is located. In the main method, we will create an instance of the multithreading example class. Finally, we will start the thread by calling the start method on the instance of the multithreading example class. Multithreading in Java allows you to perform multiple tasks concurrently, improving the efficiency of your program. To create a thread in Java, you can either extend the thread class or implement the runnable interface. When extending the thread class, you need to override the run method. This method contains the code that will be executed when the thread is started. To start the thread, create an instance of the extended class and call the start method. Alternatively, you can implement the runnable interface and provide the implementation for the run method. Then, create an instance of the class implementing the runnable interface and pass it as a parameter to the thread constructor. Finally, call the start method to start the thread. Both approaches allow you to define the behavior of the thread by implementing the run method. Make sure to provide a clear explanation of the logic and purpose of the code. To create a thread by extending the thread class, you need to create a class that extends the thread class. Override the run method in the extended class. This method should contain the code that will be executed when the thread is started. In the main method of your program, create an instance of the extended class. Call the start method on the instance to start the thread. Ensure that you provide a clear explanation of the logic and purpose of the code in your narration. In this slide, we will discuss the need for thread synchronization and techniques such as synchronized blocks and methods. Thread synchronization is important in multi-threaded programming to ensure that multiple threads can access shared resources safely. When multiple threads try to access and modify shared resources simultaneously, it can lead to data inconsistency or race conditions. To address this issue, we can use synchronized blocks and methods in Java. A synchronized block is a section of code that is executed by only one thread at a time. To use a synchronized block, we need to provide an object as a lock or monitor. When a thread enters a synchronized block, it acquires the lock associated with the object. Other threads that try to enter the same synchronized block have to wait until the lock is released. Synchronized methods, on the other hand, are methods that are declared with the synchronized keyword. When a thread calls a synchronized method, it acquires the lock associated with the object and other threads have to wait. Using synchronized blocks and methods helps in achieving thread safety and preventing race conditions in multi-threaded programs. It is important to understand and use these synchronization techniques effectively to write reliable and concurrent code in Java. In this code snippet, we will demonstrate the need for thread synchronization and the use of synchronized blocks and methods. First, we define a class called thread synchronization example with a private integer variable count. The increment method is declared as synchronized, which means only one thread can execute it at a time. Inside the increment method, we simply increment the count variable. Next, we define a run method that will be executed by multiple threads. In the run method, we have a loop that increments the count variable 1000 times. Now, let's move to the main class where we create an instance of thread synchronization example. We create two threads, thread 1 and thread 2, that will execute the run method of the thread synchronization example instance. We start both threads using the start method. To ensure that both threads finish execution before printing the count, we call the join method on both threads. Finally, we print the value of count, which should be 2000 if thread synchronization is correctly implemented. By using synchronized blocks and methods, we ensure that only one thread can access the increment method at a time, preventing data inconsistency. It is important to understand and use thread synchronization techniques like synchronized blocks and methods to ensure the correctness and reliability of multi-threaded programs. In this slide, we will explore the concepts of concurrency, deadlock, and race conditions in multi-threaded applications. Concurrency refers to the ability of multiple tasks or threads to execute in overlapping time intervals. Deadlock occurs when two or more threads are blocked forever, waiting for each other to release a resource. Race conditions occur when multiple threads access and manipulate shared data concurrently, resulting in unexpected and inconsistent behavior. Understanding and managing these concepts is crucial for developing robust and efficient multi-threaded applications. To understand the concepts of concurrency, deadlock, and race conditions in multi-threaded applications, let's consider this code snippet. We import the necessary classes for managing locks in Java. Next, we define a class called Multithreading Demo. Inside this class, we declare a private static lock object called lock, which will be used for synchronization. We also declare a static variable called count, which will be shared among multiple threads. In the main method, we create two threads, T1 and T2. The first thread, T1, locks the shared lock object and increments the count variable by 1. The second thread, T2, also locks the shared lock object, but it decrements the count variable by 1. Both threads release the lock after performing their respective operations. Finally, we start both threads by calling their start methods. This code snippet showcases how concurrency, deadlock, and race conditions can occur in multi-threaded applications and the importance of synchronizing shared resources to prevent unexpected behavior. In this slide, we will discuss the topic of using thread pools and executors to manage and reuse threads in Java applications. Multithreading in Java allows multiple threads to execute concurrently in a single process. However, creating and destroying threads can be expensive in terms of system resources. To overcome this issue, we can use thread pools and executors. A thread pool is a collection of worker threads that can be used to execute tasks. Instead of creating a new thread for each task, tasks are submitted to the thread pool for execution. The thread pool manages the lifecycle of the threads and allows them to be reused for multiple tasks. This reduces the overhead of thread creation and destruction, resulting in improved performance. In Java, we can use the executor framework to create and manage thread pools. The executor framework provides a high-level API for working with thread pools and executing tasks. It abstracts the details of thread creation and management, making it easier to write multi-threaded applications. There are different types of executors available, such as fixed thread pool, cached thread pool, and scheduled thread pool. Each type of executor has its own characteristics and is suitable for different use cases. By using thread pools and executors, we can optimize resource usage and improve the scalability of Java applications. It allows for efficient management of threads and ensures that tasks are executed in parallel. Now let's take a look at a code snippet that demonstrates the usage of thread pools and executors in Java applications. First, we create a new thread pool using the executors new fixed thread pool method. This method takes the desired number of threads as an argument. In this example, we are creating a thread pool with 5 threads. Next, we submit tasks to the thread pool for execution using the executor submit method. The submit method takes a runnable or callable object as an argument. In this code snippet, we are submitting instances of the task class, which implements the runnable interface. Each task represents a unit of work that needs to be executed concurrently. Once all tasks have been submitted, we call the executor shutdown method to shut down the executor. This ensures that all tasks are completed before the program exits. By using thread pools and executors, we can manage and reuse threads in a more efficient way. It allows us to parallelize the execution of tasks and improve the performance of our Java applications. In multithreading, communication between threads is important for synchronization and coordination. Java provides techniques like wait and notify for achieving inter-thread communication. Multithreading in Java allows multiple threads to execute simultaneously within a single program. One way to achieve inter-thread communication is by using the wait method. The wait method causes the current thread to wait until another thread notifies it. Here is an example of how to achieve communication between threads using wait and notify in Java. First, we define a class called threadCommunicationExample which has a main method. In the main method, we create an instance of the message_printer class called printer. We then create two threads, T1 and T2, using the thread class and pass them instances of anonymous runnable classes. In the run method of T1, we synchronize on the printer object using the synchronized keyword. Inside the synchronized block, we call the wait method of the printer object. This causes the T1 thread to wait until another thread calls the notify, or notify all, method on the printer object. After waiting, T1 calls the print message method of the printer object. In the run method of T2, we synchronize on the printer object. Inside the synchronized block, we call the print message method of the printer object. Then, we call the notify method of the printer object to wake up the waiting T1 thread. Finally, we start both threads T1 and T2 using their start methods. In Java, a thread is a basic unit of execution. It has its own call stack and program counter. The lifecycle of a thread consists of several states, including new, runnable, running, blocked, and terminated. The new state represents a thread that has been created but not yet started. The runnable state indicates that a thread is ready to run and is waiting for the CPU to execute it. This is just an overview of the thread lifecycle. We will discuss each state in detail in the upcoming slides. Here is a simple example of creating and starting a thread in Java. We define a class named threadExample and a main method. Inside the main method, we create a new thread object and override its run method. The run method is where the actual code to be executed by the thread should be placed. In this example, the run method simply prints a message. Finally, we start the thread by calling its start method. This will execute the run method in a separate thread of execution. You can try running this code to see the output. Keep in mind that the output may vary since threads can be scheduled and executed in different orders. That's it for this code example. We will cover more advanced topics in the upcoming slides. In this slide, we will discuss how to use the join and sleep methods to control thread execution and timing. The join method is used to wait for a thread to complete its execution. It can be useful when we want to ensure that a thread has finished its work before proceeding. We can also use join to synchronize multiple threads by waiting for one thread to complete before starting another. The sleep method, on the other hand, is used to pause the execution of a thread for a specified amount of time. This can be useful when we want to introduce delays or timeouts in our program. However, it's important to note that sleep does not release any locks or resources held by the thread. By using join and sleep effectively, we can control the execution and timing of threads in our program. This can be particularly useful in scenarios where thread synchronization or coordination is required. However, it's important to use these methods judiciously, as improper usage can lead to performance issues or deadlock situations. In this code snippet, we have an example of how to use the join and sleep methods in Java. First, we create two instances of the thread class, each with a runnable object. These threads are then started using the start method. Next, we use the join method to wait for the threads to complete their execution. This ensures that the main thread waits for thread 1 and thread 2 to finish their work before proceeding. Finally, we catch any interrupted exception that may occur during the join method call. In the run method of the myRunnable class, we simulate some work by pausing the execution of the thread for 1 second using the sleep method. After the sleep time has passed, the thread completes its work and prints a message. By using join and sleep effectively, we can control the execution and timing of threads in our program. This can be particularly useful in scenarios where thread synchronization or coordination is required. In order to ensure thread safety in Java applications, we need to address the issue of multiple threads accessing shared resources. Multithreading in Java allows for the simultaneous execution of multiple threads, which can lead to race conditions and data inconsistencies. To prevent these issues, we can use the volatile keyword. The volatile keyword is used to declare a variable as volatile, which means that its value may be modified by different threads. When a variable is declared as volatile, any changes made to it will be immediately visible to other threads. To understand how to ensure thread safety in Java applications and the use of the volatile keyword, let's consider an example. In this example, we have a class called ExampleThread that extends the thread class. We have a volatile Boolean variable called running that is used to control the execution of the thread. The setRunning method is used to set the value of the running variable. Inside the run method, we have a while loop that continues executing as long as the running variable is true. To start the thread, we create an instance of the example thread class and call the setRunning method with the value true. Finally, to stop the thread, we call the setRunning method with the value false. By using the volatile keyword, we ensure that any changes made to the running variable are immediately visible to other threads. This helps in ensuring thread safety and preventing data inconsistencies.